Alright, so this is the third video in chapter 13, and I did the other videos last week, so I can't remember if I pointed out that in chapter 12, basically what we did is we found out about different ways to write acceleration. For instance, we looked at tangential and normal components, and we were able to express the acceleration using those two unit vectors. We also expressed acceleration in rectangular coordinates, and that's just x, y, z. And then finally, we looked at polar and cylindrical coordinates and how we could express the acceleration in those coordinates. And obviously, we also looked at velocity expressions as well. But I think what can really make chapter 13 pretty easy to access is if we think about in chapter 13, essentially what we're focusing on is F equals ma, and using forces to be able to express mass times acceleration. But then we're going to look at it from the point of view of using different coordinate systems. So, when we use the unit vectors that represent tangential and normal acceleration, we would look at tangential and normal forces. Or if we're looking at cylindrical coordinates, we would be looking at the forces that are in the radial, the theta direction, and also the z direction. And, so we're all putting it all together. And I think that makes it really, makes it a little bit easier and more accessible. So I just wanted to make sure that I pointed that out. So here in this video, we're basically going to look at some of the different coordinate systems and problems, and how we would attack them if we had to do it. Use the forces to find F equals ma, and then use the expression for acceleration to kind of work from there. So in rectangular coordinates is going to be the easiest one for us because we're really used to it. And so in this type of problem, so the guy is pushing the crate, and we want to know how hard he has to push it to make it move. And so we might start off by looking at the forces that are acting on the crate. We have the normal force, we have the weight, mg. We also have his applied force, and then also we have the frictional force, which is its coefficient of friction times the normal force. And then we would look at the forces in the x direction. Are they unbalanced so that I have an x acceleration? I would use the forces in the y direction to figure out what the normal force is, because of the applied force, you might realize that it's not just mg, but it's going to be influenced by his applied force as well. And so we would look at those forces and then, sort of substitute in here for the x direction what the forces are. And then we could eventually solve for an expression for the x acceleration, which we could potentially integrate to find out how it's going to move, find velocity as a function of time, find the position as a function of time, etc. Another example here would be, for this car, has a drag force acting on it, and so maybe if it's just moving and it only has the drag force, and we're saying that it's proportional to velocity, or maybe velocity squared, and so we would use that in the expression as well when we looked at the forces in the x direction. And essentially what we're doing is we're approaching these problems by looking at forces and then using F equals ma to write the forces and relate that to the acceleration, and then kind of move on from there. So if we start with F equals ma, and we're doing rectangular coordinates, what we're going to do is we're going to break these down into components. And so we have forces in the x direction will give x acceleration. Forces in the y direction will give the y acceleration. And if we have 3 dimensions, we can look at forces in the z direction, which will give us the z acceleration. So, by identify the forces, and if necessary, you're going to break them into components. And then you'll use these on the left-hand side of these expressions. And then finally, you can then solve for the acceleration, the x, the y, and the z. And then, of course, these can be integrated. To get more information. So here is an example. So here we have a crate that's being moved up an incline, and we're told it moves a certain distance in 3 seconds starting from rest, and we're also told what the coefficient of kinetic friction is. And so let's use this to figure out how to approach this problem. So we remember that in an inclined plane, we put the x-axis along the inclined plane, and then the y-axis is perpendicular to it. And again, because we're going to look at forces in the x direction, which will yield an acceleration, and forces in the y direction, which in this case would add up to be 0, because we don't expect the crate to be moving up and down. Using that as our guide, we have to identify what our forces are that are important in this problem. So we start to label forces. We have the weight of the crate, which is mg, and we have the normal force, and we have the tension in the cable, and we're also going to have a frictional force. So those are the forces that we would have. And so in the x, let's do y direction first, because it's always nice to figure out what the normal force is. We have normal minus mg cosine theta equals 0. So our normal is mg cosine theta. Remember that this angle is theta, which is the same as this angle. That's how it works for an inclined plane. In the x direction, we have the tension minus the y component of the force, and then the friction gives us our mass times our x acceleration. We know that we can express our friction as the coefficient of friction times the normal. And then we know what the normal, I should have used the same, I should have used capital N there. The normal force we already found from the other expression. And so you can see that we're really close to being able to figure out some information here. Now, what we've been asked to find here is the tension. And so if I look at my expressions, if I sort of solve for tension here, I see that basically everything I could just literally plug and chug, except I don't know the acceleration. But they did give me some information. They said that the object moved 6 meters in 3 seconds starting from rest. And we're also told it's a constant acceleration. So I happen to remember my constant acceleration expressions. And so I noticed that because it starts from rest, and I know that it moves 6 meters in 3 seconds, it's going to be pretty straightforward to find the acceleration. And then once I have that number, which I don't have my calculator handy, I can plug it in there and I can figure out what the tension is. Okay? So this is an example of how we might be putting it all together. To be honest, this problem might not seem all that different than ones that you've done probably in general physics. If we look at the next example, which we're going to, I did everything on one piece of paper, so that was okay. In this problem, we might be a little bit more likely to be using our information here. So in this problem, we have this problem is a little bit more sophisticated in terms of how we might do this. Here, we're told that there's a force on the cable, but notice the force is time dependent. We're not saying anything about friction, and so we have to assume that there's just the weight acting downward. And notice this information is going to help us find theta, or just use for sine and cosine. And so we could write, and we also have a normal force we don't want to forget. But if we looked at the forces in the x direction and set them equal to mass times acceleration, and then what they're giving us is information to figure out, we're given the v naught, and we want to find the velocity and position when t equals 2. So what they want you to do is figure out an expression for the acceleration, then express that as dv dt, and integrate to get velocity as a function of time, and then also integrate to get position as a function of time. And so that's something I'm going to leave for you to do on your own, and we'll come back when we meet as a group and talk about that together. All right, so keeping with it, we might want to look at situations where we have normal and tangential coordinates. If you remember, we talked about those in the last chapter. If we're following an object along a curved path, we could always express things in terms of the direction that's tangent to the path and also a direction that's normal to the path. So one example of that might be as we follow a satellite around the Earth. We can think about its tangential and normal accelerations that it might have, and we could view things from that point of view. Keeping in mind, here's a picture of where we have the tangential. So we could, again, then we would split up the expressions of the sum of the forces. We would have the tangential and the normal would be our two coordinates. It's nice to have a three-dimensional with mutually perpendicular unit vectors, and so this unit vector here would be perpendicular to the plane of the object, which a lot of times we don't have to worry about if we can view things all in the plane, and those are the only forces that we have. And sometimes it's not going to be possible. And so remembering that the normal coordinate points towards the center of curvature, and so if we were over here, the center of curvature would be switch sides. We learned about that in the last chapter. And so I think we can, so if we look at the equations of motion, so breaking down F equals ma, we can have the sum of the tangential forces equals the mass times the tangential acceleration. The sum of the normal forces is equal to the mass times the normal acceleration, and then finally the sum of the forces in the b direction are equal to the mass times acceleration in the b direction. And that's how we would kind of cut it up. And then we would look at the components of the force, just as we did with rectangular, and put them into the expressions to find expressions for the acceleration in the normal and the tangential direction. So look at, the other thing that I forgot about is we did talk about when we look at the acceleration for the curvilinear path, remember that we have the centripetal acceleration and the tangential acceleration. The centripetal acceleration uses the radius of curvature, which for whatever reason is in white font, which does not show up, but there's an expression of how we can find the radius of curvature for a particular curve. It's dependent on the shape of the curve. And if we know the function y is a function of x, we can use this expression to find the radius of curvature. There's a particular problem where you'll see how you could use that. A lot of times we're used to things that basically look like circles, so you just use the radius of the circle. But that's not necessarily always going to be the case, and sometimes you're going to have to find the radius of curvature for a particular curve that you're working with. Okay, so here's an example where we could use the forces in the tangential direction and the forces in the normal direction. So here we have a ball suspended on a cord, and so we have the tension in the cord, and we have the weight acting straight down. And so the direction, this would be the normal direction, and this would be the tangential direction. So if we looked at forces in the normal direction, we would have the tension, if we say in towards the center is positive, and then we have mg, this angle is going to be 45. It's easy because it's 45. Cosine of 45 equals the mass times the normal acceleration. And so we could set that into equal to mv. The normal acceleration is centripetal, and so that's going to be the velocity squared over the radius. So we can set those equal to each other. In the tangential direction, we just have mg times the sine of 45 degrees equals a tangential. So we could solve this by this equation allows us to find the tension, and then this equation will allow us to find the tangential acceleration, which is the increase in the speed of the ball. And so that's how we would approach that problem. This is a problem that's a little bit more complex because we're looking at this instant in time at normal and tangential, and we're also going to need to find the radius of curvature. And that you can use the expression that I found that I showed you a couple slides ago, and here is the function that can help you with that. So this one's a little bit more involved, and this is one that I'd like you to try to work on your own for whenever we meet to discuss this chapter. And then the last thing that we're going to look at is the idea of, well, we sort of did polar coordinates in conjunction with cylindrical coordinates. And so again, we can sort of put those together, polar coordinates being when things can just be expressed in a two-dimensional plane, and cylindrical when it is a three-dimensional situation. But again, what we're doing is we're using those different coordinates and those unit vectors to separate the forces into those different components and also the acceleration in those different components. So for instance, this little boy going down the slide, this might be a really good opportunity to use cylindrical coordinates because he's going in a helical pattern, so he has probably a constant radius, but his angle is changing over time, but he's also changing his vertical distance. And so we could think about the forces that are acting on him, and it would really fit in very nicely with using our cylindrical coordinates, where we would be using r, theta, and z, and so that we would look at the forces in the radial direction, the forces in the theta direction, and the forces in the z direction, setting these equal to MAR, MA theta, and MAZ. And here, for whatever reason, I think this was a font thing, so here Q is really taking the place of theta. But these are the expressions that we learned about in the previous chapter. And so, again, it's just how are we going to represent the acceleration when we're using different coordinate systems, and then using the forces to rewrite these expressions. And then we have what we call the equations of motion that can then help us get more information about the problem. And I think that is it. So, well, polar coordinates is just not using the z. All right, so that's it for that part of chapter 13.